everyone and welcome to the class. So in this particular video, I'm going to solve previous year's questions from your June 2019 CSIR NET exam. And this video, I'm going to take question from your quantum chemistry. All right. So there were 4 or 5 questions which are asked from this particular topic in June 2019 exam. So I'm going to give you a detailed solution of that. Okay. So generally, if you talk about quantum chemistry, so in CSIR NET, you will get around 4 to 6 questions from this particular topic from both the sections, like section B and section C, that is part B and C of your question paper. It carries about 14 to 20 marks weightage if you leave behind the chemical bonding part. If you just take the quantum chemistry part, so it will give you around 14 to 20 marks from this particular topic. And the difficulty of the questions are from moderate to difficult. Okay, so you would get questions which can be moderate as well as difficult questions from this particular topic. And it is very important topic. If you are a math student, you should be very good at it. If you're a non-math student, you should be at least good at the basics of your quantum chemistry. All right, so I'll be taking questions. So on that note, this is the first question which was asked in your June 2019 exam. And the question was asked as like, for a particle of mass small m in a one-dimensional box of length 2L, the energy of the level corresponding to n is equals to 8 is. Okay, so now this particular question was asked from your particle in a box problem. Okay, so it was already given that the mass of the particle is m and the length of the box is 2L, right? And it was asked that what is the energy of the particle if value of n is equals to 8. So we all know that the formula to calculate energy of a particle in one-dimensional box is E is equals to n square h square upon 8 ml square. All right. So this particular formula is given if the mass is already given to you as small m and if the length of the box is taken to be capital L. Now, since in the given question and also n is the energy level for which we are talking about. Okay. So now since in the question we are given with the values, so we'll just substitute those values. So for the given particular question, we have to put L is equals to 2L, right, which is given to us in the question. Also, we have to put N is equals to 8 and M is M as it is. So we are not going to do anything with that. So we just have to substitute all the values over here. So we'll get E8 because it's for the 8th energy level. So we'll get 8 square h square divided by 8m and it will be 2L square. Okay, basically it should be 2L whole square. All right, so now you just have to solve it mathematically. That's it. So you are going to get 8 into 8. I can just write down this 8 square as it, and into h square divided by 8m into 4L square, because square of 2 is 4 and obviously L square is L square. Now you can cancel out this 8 with this 8 and this 4 will cancel out this 8 2 times, right? So the answer which you will get will be 2h square by ml square. So if you look upon the options, so the correct option comes out to be your option number 4. So that is how you will get the correct option for this particular question. All right. Let's talk about the next question which has been asked from quantum chemistry in the exam. The previous one was from your particle in one-dimensional box. Now the other question over here is from your variational theorem. Okay, so the topic of this particular question is variational theorem. Okay, so what does the question say over here? So the question says that the energy functional from a trial wave function is given to you by this particular equation, that is E alpha is equals to alpha square minus 3 alpha by 6. The variationally optimized energy is, okay, so they are asking about the variationally optimized energy. What does this optimized energy means? So basically optimized energy is nothing but either the minimum value of the energy or the maximum value of the energy. Okay, that's what the optimized energy basically means. So when you will get a minimum or the maximum value, so basically this is from a mathematical or a calculus point of view. The question is from the calculus point of view. Like the maxima or minima of a particular function you can get just by differentiating it, like just by doing it a first differential and just by equating it with equal to 0. Okay, so what you have to do is you are given with the function, you just have to equate it, you just have to differentiate it first of all and then equate it with the equal to 0. That's all you have to do. and you have to find out the value of alpha, put it back to the energy, and you will get the optimized energy value. So we'll do that. Okay, so the energy functional is given to us, that is E. I'm not going to write down E alpha. E alpha just suggests that it's a function of alpha, right? So E is equals to alpha square minus 3 alpha by 6. That's what the value is given to us. Or I can also write it like 1 by 6 alpha square minus, it will be 3 by 6 alpha. Okay, so I can write it in this way as well. Now what I'm going to do is I'm going to differentiate this particular function with respect to alpha, because it's a function of alpha, obviously. So it will become dE by d alpha. Okay, so I'm just differentiating once with respect to alpha. So what I'm going to get is 1 by 6 is a constant, so that will remain as it is. Differential of alpha square is going to be 2 alpha, just like differential of x square is 2x. In the same way, differential of alpha square will be 2 alpha. 3 by 6 I can write down as 1 by 2, so I'm going to write down 1 by 2, and differential of alpha is going to give me 1. Alright, just like differential of x, d by dx of x is equals to 1. In the same way, d alpha by alpha is going to give me 1. So this is what I'll be getting. So I'll just write down over here in the other side. So dE by d alpha is going to be this you can cancel out. So it will be 1 by 3 alpha minus 1 by 2. So this is what I am going to get. Now what I have to do, I just have to equate it equal to 0. So I'll just take it equal to 0. I just have to solve this much part to get the value of alpha. That's it. So I'll take it to the other side. So I'll get 1 by 3 alpha is equals to 1 by 2, or I can say that alpha is equals to 3 by 2. So this is going to be the value of alpha which I will get. Now this is the value of alpha at which energy will be either maximum or minimum. Now in order to find out whether it will be maximum or minimum, you can go one more step further. You can just double differentiate that. If you get a negative term on double differential, that will be maximum value. That is going to tell us that okay, this alpha is going to be maximum. And if you double differentiate and you get a positive value at this particular alpha, then you say that okay, this alpha is the minimum value of that. Now in this particular question, we don't have to find out maxima or minima. Okay, we just need to find out the optimized. That means either maxima or minima. So we don't have to go to the further step. We just have to put this value of alpha in this particular equation of energy to get the optimized value of energy. That's all we have to do. So I'm just going to substitute the value of alpha in this particular function. So what I'm going to get is this, that is E, and the alpha value is 3 by 2. So I'll just write down E 3 by 2. That means the value of energy at alpha 3 by 2. That is going to be, I'm going to use this equation. Okay. So this will be 1 by 6, alpha is 3 by 2 square. All right. And minus this is 1 by 2 and alpha was 3 by 2. Alright, so when I will solve this is going to be 1 by 6 into 9 by 4 and minus 3 by 4. Alright, so I can just simply solve it. So it is going to be 2 times, 3 2 times, and 3 3 times. So this will be 3 by 8 minus 3 by 4. You can take LCM and solve it. It is going to give you, since it's a bigger term, so this will be minus 3 by 8. So this is how you will get the answer of energy at 3 by 2 alpha value as minus 3 by 8. So minus 3 by 8 is going to be the variationally optimized value of energy. So correct option is going to be your option number 2. Alright, so that's how you have to solve this. Remember what I have done? I have just taken the equation given to me in the question. I have just differentiated once. Okay, I have just differentiated that equation once. Equated equal to 0, calculated value of alpha, substituted that value in the equation given to me, and just calculated the optimized energy. Okay, so any question related to that, you'll find the similar question in the previous year June 2015 exam. Okay, so similar kind of question has been already asked in CSIR NET. All right, so as we have done with this particular question, let's go to the next question then. Okay, so this particular question, it says that satisfactory spin wave function of an excited helium atom is. So they are asking about what, like, among the given option, which is a satisfactory spin wave function for the excited helium atom. Okay, now this particular topic is from your Slater's determinant. Okay, so this particular thing, okay, fine. So how we'll do that? So in the Slater's determinant, you might have studied that there are two parts it's written in this way, that is 1 upon n factorial, and it's a spin function, okay, spin function, and into your spatial function or a spatial part. Okay, so this is the way how we write down wave function for a multi-electron system. Okay, so this particular like it has two parts. It has a spin part, also it has a spatial part. Now there are many rules which you have to follow in order to write down a wave function. The first rule says that that any of these two part, either spin part or a spatial part, has to be antisymmetric. That means any one of these two part has to be antisymmetric. Now, since we are talking about helium in the excited state, that means the electronic configuration would be okay. So let's talk about helium. So helium has 2 electrons. In the ground state it will be 1s2, but helium in the excited state will have electronic configuration of 1s1 and 2s1. That means both the electrons will be in different orbitals, right? One will be in the 1s orbital and the other one will be in the 2s orbital. Now that means the spatial part will be symmetrical. You have to deal with the spin part. Okay, so how you can write down the spin part? Let's do that. So what are the possibilities of writing the spin part? So fine, let me just make it up. So let's say there are 4 possibilities, since these electrons are in 2 different state, like 2 different orbitals. So I'm just drawing those 2 orbitals or those 2 energy level. This is 1s and this is 2s, the excited level. Okay, and I will fill the electrons in this way. So I can have my electrons like this, either both of them in the positive spin or both of them in the negative spin, or one in the positive and the other one in the negative spin, or the first one in the negative spin and the other one in the positive spin. So these are the 4 possibilities of the spin part which we have. Since we just have to deal with the spin part in the question, so that's why I have just taken the spin part. Okay, although you can do the spatial part as well, but that is not that we don't have to do from the quotient point of view. So I'm just sticking to the spin part only. Okay, so for the sake of like in order to represent these spin parts, what we do actually is we write down the positive spin as alpha spin, okay, and the negative spins as the beta states. Okay, so remember this, that if the spin is up, this is called as the alpha spin. If the spin is down, so we call it as beta spin. Okay, so beta is the spin down state and alpha is the spin up state. So what will be what will be your spin states over here? So this will be called as alpha 1 and alpha 2. Why so? Because this is also in the spin up state, this is also in the spin up state. So both in the alpha states. So that's why alpha 1, alpha 2. That means, what does it say? That first electron in the alpha state or in the spin up state, and alpha 2 means the second electron also in the alpha state, okay, or in the spin up state. What about this one? This will be called as beta 1, beta 2. The same way. The one, like here both the spins are in the downwards. Okay, so this will be called as beta 1, beta 2. What about this one? Here we will call it as alpha 1, beta 2. Why? Because the first electron is in the alpha state, the second one is in the beta state. And for the last one, we'll call it as beta 1, alpha 2. So what we have to take care of is that total wave function has to be antisymmetric. So that will be done if any two of them will become, if any of these two become antisymmetric, right? Now the spatial part for the helium in excited state will be 1s1 and 2s2, okay, because first electron is in 1s state and second electron is in the 2s state. So this is a symmetric wave function. This will be spatial part, okay, this will be the spatial part, and this is symmetric. You can see from here as well, okay, symmetric. So this is a symmetric wave function. Now the other part has to be antisymmetric. So right now all these spin parts are symmetric, okay. In order to make them antisymmetric, you have to either add or subtract them. So you can see the addition is only given in the other ones, right? There should be alpha, okay. So the only in the other ones. So how we will do that? We can just do that by adding these last two, okay. So although you can make the others also, but those will make a symmetric spin part. Symmetric spin part we don't need. We need an antisymmetric. Why? Remember, your psi total, okay, total wave function has to be antisymmetric, okay. and in order to make it antisymmetric, either your spatial parts has to be antisymmetric or the spin part. Now spatial part is already symmetric because it will be written in this way, so it is already symmetric. So spin part has to be antisymmetric. So how to make that antisymmetric is just by like in the option, if you see, the only antisymmetric spin part is your option number 1, where these two spin parts are getting added. Okay, so alpha 1 beta 2 plus alpha 2 beta 1 is going to be the answer. Now if you look upon option 3, you might think that okay, why is not this one is not correct, because both of these parts are same, alpha 1 beta 2 alpha 1 beta 2. So if you, that means both of these are same states. Now you cannot add two same states and make it antisymmetric. Okay, you have to add two different states in order to make an antisymmetric wave function. Okay, so these are these things you will understand in more detail if you read books related to this particular variational related to this Slater's determinant. And for that I'll suggest you to follow either Macquarie or Levine to deal to study these things in more detail. Okay, so this option number 1 goes to be the correct option, because this part is antisymmetric part. Now why is this under root 2 written? Because you are having 2 electrons, and remember I have told you that it's under, so it should be under root n factorial. Now this n is the number of electrons over there. Okay, so since we have 2 electrons, so that's why it's under root 2. All right, so that's how your option 1 becomes your correct choice for this particular question. All right, so let's look upon this particular question. It says that the highest energy p, or should be pi, okay, the pi molecular orbital of the allylic system. So what it will be? So this particular question is from your Huckel molecular orbital theory. Okay, Huckel molecular orbital theory. Now in the Huckel molecular orbital theory, if you look, so they are talking about the allylic system. What is allylic system? Allylic system is anything, so it can be either, like this is allylic system. Okay, it can be either carbocation, it can be either carbon, and it can also be a free radical. So this is allylic system. I'm just taking for now a carbocation, allylic carbocation. Okay, so we can do question based upon it, like just by taking this as example. Okay, so the highest pi molecular orbital, how to draw that? First of all, there are 3 carbons, so obviously there will be 3 energy levels, right? So this will be called as psi 1, this will be your psi 2, and the other one will be psi 3. Okay, now you just have to make the lobes. Okay, so remember how to make the lobe. So since in the psi 1 this is the lowest energy state, so the number of nodes, okay, I'm just writing number of nodes, that will be 0 over here. N is the number of nodes over here. Okay, so 0 nodes over here. So how to draw these orbitals? So the orbitals will look something like this. Okay, the orbitals will be something like this. So this is for 0 nodes. Now here I'll be having 1 node. So the 1 node will look something like this. It will be at the center over here, and this will be drawn something like this. Okay, so this is the node over here. Now in the energy level 3, or in the psi 3, I'll be having in the wave function 3, or the molecular orbital 3, I'll be having 2 nodes over here. Okay, 2 nodes will be made somewhere over here, one over here, the other one over here. Now if you just make the nodes properly, so this is how you will make that. Okay, all right, how to find out the number of nodes? I'll just tell you in a very brief way that the number of nodes is 1 less than the orbital for which you are talking about. If you are talking about the 3rd orbital, so 3 minus 1 is going to give you the number of node for that orbital. Okay, fine. So this is how we made it. Now in the question we were asked about the highest energy pi molecular orbital. So as you can see that the highest energy, okay, from the energy level, if you look, so this is the highest one. Okay, so this is the highest energy pi molecular orbital. How many nodes are there in it? So you can see there are 2 nodes. You don't have to do anything. You just have to look upon the options. You have to see that where you are having 2 nodes. How to identify nodes in the form of when it is given in the form of equations? So you just have to see that how many times your sign changes. Okay, your sign changes how many times, that's all you have to see. So if the sign changes once, that means you have 1 node. If the sign does not changes, that means 0 nodes, and like that. Okay, so in the option number 1, if you see, there is no change in the sign, everywhere it's plus plus plus, so that means the number of nodes will be 0 in this case, in the first option. In option number 2, if you see, there is just once when the sign changes, so the number of node is actually 1 over here. If you look upon option number 3, so here the sign changes, like it was plus, it became minus, and again it became plus. So once and twice. So the sign changes twice. So that means there are two nodes over here. And in option number 4, if you see, this was plus, it became minus, then again it remained minus only. So the sign changes just once. Okay. So n is equals to 1. Now we have to find out, we were about to find out the highest energy orbital, right? The one which was having two nodes. In the option, you can easily see which option is having two nodes. So you don't have to do anything, right? Option 3 is going to be your correct option. This type of questions are very, very simple to do in the exam, and they are just very simple. Okay, you just have to draw, you just have to see the number of nodes in the orbital which is asked. You just have to look upon the options and you just have to mark. That's it. Okay. If in this particular question in the allylic system, instead of allylic system, they would have given allylic carbocation, and they would have asked for the HOMO. Okay, so for the carbocation, your HOMO would be psi 1, right? So in that case, which would be the answer? So the answer would be option number 1 in that case, because there was no node in that. Okay, so that is how you can solve questions related to that. I hope whatever I have explained in this video, it was like you guys understood that and you guys got everything well, right? So yeah, that's all for this video. I have just covered 4 questions which are asked from quantum chemistry in this particular, in the June 2019 exam. So I'll just conclude all the things which I have like whatever questions I have solved. So the level of question, I would say it was easy. Okay, the question were quite easy. Like we were having 2 easy questions. Okay, the last one was easy question, as well as the one where we did maxima and minima. That was all, or the first one was easy, right? Where we were doing that particle in a box question. So those 2 questions were easy, and 2 questions were, like, I would say they were difficult. Okay, so 2 questions were difficult. Which 2 questions were easy? So the first question and the 4th question which we did in the video, they were easy question, whereas the second and the 3rd question, they were difficult. Okay, now the concepts which were used in the first question, it was particle in a box. Okay, particle in a box. That was used in the second question. If I remember, it was variational theorem. Variational theorem was used. In the third question which we discussed, what was used? Yeah, they have used Slater's determinant. Okay, so Slater's determinant. And in the last question, they have used Huckel molecular orbital theory. Okay, so these were the concepts which were used in the question solved, and some useful tips. I would say that at least from quantum mechanics, these topics which I have done, just read about these topics and try to do the theory of it and try to practice as many as questions. Okay, so practice questions and especially your PYQs. Okay, so try to practice your previous year's questions based upon quantum chemistry. It is going to help you a lot, because many times questions are repeated, not exactly, but yeah, the concepts are repeated. So that's all for this video, guys. Thank you so much for watching. I hope whatever we discussed in this particular video was helpful to you. You guys understood everything well, and that's all from my side. Thank you so much for watching.